Hi everyone, welcome back to PW English Medium channel. Friends, as you know, we are continuing our UMEED NEET English batch. In this batch, we are going to complete each and every chapter in one shot. In these one shot lectures, we are going to complete the theoretical part as well as the numerical part, right? So till now, we have completed till center of mass. If you haven't watched some of the chapters, or if you have missed, please find those chapters in the playlist. You can watch these chapters, you can watch these classes on our YouTube channel as well as on our PW app, and it is absolutely free, right? So today's class is going to be it's going to be for rotational motion, which is actually nothing but it is an extension to center of mass. As you know, in NCERT, both of the chapters are combined and combined by the name system of particles, right? So rotational motion, you might be knowing this, it's a big chapter. So you need to understand one thing, that whenever we are going to actually study any chapter, we have to keep one thing in mind, that in how much of time I should be able to actually complete that chapter. You should ask this question to yourself, right? And the second question is, how many questions actually come in NEET exam? So even if, let's say, if you think that okay, rotational motion is actually quite difficult, it is one of the most difficult chapter in mechanics, and you're a little bit afraid about all of these things. So let me tell you, as far as NEET is concerned, rotational motion is it's not going to create any problem for you, right? All you need to do is you need to keep your basics really strong. You need to complete each and every chapter. You need to actually remember all the important formulas and all the important moment of inertia things, and plus I mean, having said all of these things, you must also have good practice over questions. That's all. You don't need to really solve many hard problems. You really don't need to actually study this chapter for like straight 15 days or like 20 days. Nothing's going to make a difference for your NEET exam, right? You might feel really good that okay, now I have actually successfully I have studied this chapter for 20 days. It's not going to make a difference. Set up a timeline that okay, from this to this day I'm going to complete this chapter. I'm going to complete each and every chapter conceptually, each and every topic conceptually, right? So having said all of these things, let's start today's class. In today's class, we are going to cover each and every topic, and those topics are these. First, we are going to discuss what do we really mean by rigid body. Although if you remember, when I was talking about center of mass, which was our previous chapter, we touched this topic, that what do we really mean by rigid body, what do we mean by particle body. Then we are going to talk about types of motion. In types of motion, we are going to discuss all three types of motion, which are pure translational, pure rotational, and combined translational plus rotational, which is also called as rolling motion. So when I said that you need to actually complete each and every topic conceptually, this is what I meant. This is what I mean, that please always remember the definition of these things in their true meaning, right? So you really don't need to actually mug up the definition. All you need to do is you need to actually really understand what do we really mean by pure translational motion, what do you really mean by pure rotational motion in its true sense, right? What do I mean by true sense? Whatever the technical definition is, whatever the absolutely correct technical definition is, we need to remember that, right? Then we are going to of course talk about moment of inertia. After moment of inertia, in this part we are going to first discuss what do we really mean by moment of inertia. Again, the definition, the concepts are going to be really important for us, all the theoretical concepts. Then after that, we are going to talk about moment of inertia of system of particles, of a single particle, of system of particles. Can you draw a comparison from center of mass? Exactly, that's what we did in that chapter, right? We talked about center of mass, then we talked about center of mass of discrete system of particles. Then we discussed center of mass of continuous of bodies which has got continuous mass distribution. Similarly, over here as well, we are going to talk about those things again. Then moment of inertia of rod and plate. I have written two things. We'll discuss for a disc, right, or a solid cylinder. Then we have got two theorems which are really important for rotational motion, for moment of inertia, which are theorem of parallel axis and theorem of perpendicular axis. We are going to do that, radius of gyration, torque. Then when I am saying torque, that means we have started the the thing that we have learned in kinematics. Do you remember? First equation of motion, force F equals to ma, all the dynamics thing that we have done. We are going to again talk about all of those things, but this time we are going to talk in sense of rotational motion. Then last part is going to be rolling motion. Obviously there are going to be many more topics which I have actually assumed that those topics are going to be inside of these ones, right? So let's start our class with what do we really mean by rigid body, right? What is the definition of a rigid body is? So definition of a rigid body is quite simple. I have actually written it in front of you. Rigid body is defined as a system of particles in which the distance between each pair of particles remains constant, right? So distance between the each pair of particles remains constant, all right? So I mean, till now, what were the bodies? I mean, till now, when we were talking about kinematics, or when we were talking about like Newton laws of motion, what were those bodies? Were those bodies rigid body or not? So this is the first question that we can ask ourselves. See, when we are discussing about translational motion, right? I'm going to actually discuss what do we really mean by translational motion. But for now, let's just assume that you know what translational motion is. Whenever we were talking about translational motion, whether we have got a body something like this, which has got mass m, it is a block, or whether we have got a body something like this. So this is a point particle. I can just say that this is actually a point mass. So point mass is nothing but it is a body which has got no volume or negligible volume, right? So if it had no volume or negligible volume, we were really not concerned with that. Okay, it is made up of many more particles. We were not going to talk about all of those things. We said, okay, it is one single particle of mass m kept at any point, and we can write its coordinate. But now what we are saying is, we are saying that we have got a body something like this. Let's suppose we have got a body something like this, and it is made up of, let's suppose, many more particles. Like it might be made up of infinite many particles. Let's draw two particles. So I have drawn two particles. This is particle A and particle B. What this definition is trying to say is that the separation between these two particles, and let's say the separation between these two particles is represented by this dotted line. This separation is not going to change. This distance is not going to change. So this is one simple definition for you, for all of you, right? So this is the definition. Distance between each pair of particles remain constant. So I have considered one pair of particles. You can consider any pair of particle, right? I have considered one pair of particles. The distance between these two particles must not change. Now let's suppose they have got certain velocities. Let's suppose A has got a velocity in this direction and B has got velocity in this direction. Let's just consider this, right? So let's suppose in this direction. And let's say this angle is theta 1, this angle is theta 2. All right, this is VA, this is VB. So if we want to actually draw all the components of the velocities of these two particles, we are going to get something like this. So we have got VA over here. And if let's say this is theta 1, I'm going to say that this component is going to be VA sine theta 1. and let's say if this is VB, this is let's say theta 2, this is VB. In this case I'm going to say okay, this is going to be VB sine theta, sorry, this is going to be VB cos theta 2, and this velocity is going to be VB sine theta 2. And in the similar way, this component is going to be VA cos theta 1. Is it all good? See, that's what I was trying to say, that whenever you are going to start any chapter, whenever you are going to start any particular topic, the first thing that you must understand is, you have read that definition, fine. You have understood it, fine. It was quite an easy definition, right? That the separation between any two pair of particles must remain constant. It must not change. So we have considered one pair of particles. We have considered two particles A and B, and let's suppose they have got certain velocities in some random directions, making an angle theta 1 and theta 2 with the line joining them. The next thing is, we have to rewrite whatever we have to rewrite the definition in a mathematical form. So what do we really mean by distance between each pair of particles remains constant? It means that the velocity of separation, whether we are talking about velocity of separation or we are talking about velocity of approach, they must be 0. Isn't it? Because only in this case we can say that the separation between those two particles is not changing, right? So let's do the same thing. So in this case, VA cos theta 1 must be equals to VA cos theta 2. VB cos theta 2. That's it. So this is the condition for this particular example, for it to be a rigid body, right? We are going to, of course, we are going to talk about some of the examples, like for example, is a human body rigid body? Is my hand a rigid body? So in layman term, we might say, yes sir, the hand is actually a rigid body. This is the point where you must make a difference. Let's not understand these definitions in layman terms. Layman terms basically means that the meaning that an ordinary person would assume, right? Whenever we are going to talk about any term, even if you think that you know it, please cross check it again. That's where you are going to lose your marks, right? NEET exam is not that difficult. It's all about accuracy. It's all about completing your syllabus multiple times. So if we are talking about a rigid body, this is what mathematical meaning means. Can I say this pen is a rigid body? Of course, this pen is a rigid body, right? The separation between any two particles is not changing with respect to time. So this is what a rigid body basically means. After this, what about these things? What about this velocity VA sine theta 1 and VB sine theta 2? So whenever we are going to talk about a rigid body, if let's suppose we are saying that this body is under motion and these particles have a certain velocity. So we can say that the motion of, please hear me out carefully, I am saying motion of particle B with respect to A is circular. Is that correct? Can you see it? Well, if I want to find out with what velocity it is moving, I'll say velocity of B with respect to A is actually nothing but VB sine theta 2 minus VA sine theta 1. All right. So please note all of these things as well, and also you can note some of the examples like this pen is a rigid body, right? If you are learning all of these things sitting in front of a desk, that desk is actually a rigid body. So now, after learning what do we really mean by rigid body, let's move to our next topic, which is types of motion. Now, I've already told you in types of motion, we have got three types of motions. First one is pure translational motion. Now, this is the thing. If you are really talking about a pure translational motion, whether we are talking about a particle, a single particle, a point mass, or whether you are talking about a rigid body, it makes no difference, right? If we are talking about a pure translational motion. But now let's first define what do we really mean by a pure translational motion. A pure translational motion can be defined as, let's suppose we have got a body, and this time let me take a box, something like this. Again, I can say that, okay, this box is made up of many more particles. Like, let's say it is made up of particle 1, 2, 3, 4, 5, and n number of particles. And let's suppose this body was in motion. This body was, let's suppose it was moving with certain velocity of v, and after a certain period of time, it covered certain displacement, and it has covered a displacement. Let's suppose it covered a displacement of x. So it has covered a displacement of x. So this is x. So each particle, please remember what is the definition for pure translational motion. Each particle in the rigid body will cover the same displacement no matter how small or how large the time interval is. This means that this particle has also traveled x displacement. This particle has also traveled the x displacement, and similarly each one of them has traveled same displacement, right? This is very important. This means that each particle has got same velocity, right? Which means that we are going to say that for pure translational motion, v1 equals to v2 equals to v3 and so on, no matter how many number of particles are there, vn. And we have actually, we were able to write this because first we said that, I mean, their displacement are going to be same, right? So if their displacement are going to be same, then their velocities are going to be same, and if their velocities are same, we can also that their accelerations are also going to be same. So a1 equals to a2 and so on equals to an, and all of these things are going to be equals to the velocity and acceleration of center of mass. That thing holds true over here as well, right? So this is very important how we are going to actually write all of these things. And if you want to now, if you want to write any more equations, you can write about force equals to mass times acceleration. If you want to write kinetic energy of these particles, you can write half m1, you can rewrite it something like this. If you want to write kinetic energy of this rigid body, you can write half m1 v square plus half m2 v square and so on. So we can simply rewrite this thing as half m v square. So this is going to be called as now translational kinetic energy. We are going to also write a formula for rotational kinetic energy. Right now this is translational kinetic energy. So is now definition clear to all of you? Because this is actually one of the most important thing in this chapter. The building blocks are, first we need to understand the definition in their true sense. So the definition in its true sense is the displacement of every particle in the rigid body is going to be same in any time interval, right? So hopefully everything is clear. Now moving on to the next type of motion, which is actually rotational motion. And when I'm saying rotational motion, I mean to say pure rotational motion. Well, it's not something like we have got some impure rotational motion, but it means the same thing like translational motion, rotational motion, then we have got combined motion, that is rolling motion. So under rotational motion, we are going to say, now we are going to say that, okay, let's suppose that we have got a rigid body, and let me draw a random rigid body. We are going to say the perpendicular distances of these particles. Now you know which particle I am talking about. It is made up of many particles. Let's name them as M1, M2, M3 and so on, Mn. And let me draw an axis. This axis will be known as axis of rotation. So a rotational motion is that motion in which we are going to say that the perpendicular distances of these particles with an axis is going to remain the same. It's going to remain constant. So this is, let's say this is R2, this is R1, this is Rn, right? This is R3. So this distance will remain constant in pure rotational, in rotational motion, right? This is the definition for the second type of a motion, and this is known as axis of rotation. Now we can talk about all of those things that we have done in circular motion, right? That if you want to write what is the angular velocity, so angular velocity will be written as d theta by dt. So for every particle, omega will remain same. So omega 1 equals to omega 2, and of course in vector sense, so on, equals to omega n. So angular velocity will remain same, right? Angular acceleration alpha can be written as d omega by dt. This will remain same, like for each and every particle, alpha will remain same. Obviously linear velocity can be different. Other than that, you can also again rewrite those equations of motion over here. For example, as you can rewrite it as omega f equals to omega I plus alpha times t if alpha is constant. Then theta equals to omega I times t plus half alpha t square. Then omega f square equals to omega I square plus 2 alpha times theta. All of these things, right? And if you want to write now the kinetic energy of this system, then what you can do is you can actually write kinetic energy of this system as half m1 v1 square plus half m2 v2 square and so on plus half mn vn square. Now from circular motion, we know one thing, that v can be actually written as r omega, and omega is constant for each one of them. Is that correct? So this means that I can rewrite the kinetic energy of this rotational motion. By the way, this is actually rotational motion. I can rewrite this thing as half. Now please understand, for each one of them omega is constant. That is absolutely true. Each one of them is moving with angular velocity omega about this axis of rotation. So for each one of them omega is constant. So I am taking out omega over here. Now I will be left with m1 into r1 square plus m2 into r2 square and so on mn into rn square. Please take a look. I've all I have written is just half mv square, right? Half mv square, which is kinetic energy of individual particles. Then I have converted v equals to r omega. Omega is constant for for each particle. So instead of v, I have written r omega. Obviously r is different, so I have taken out omega square constant. Now if you will please pay attention, we are going to do one thing again and again. We are going to compare the rotational motion with translational motion. See, we have already studied translational motion. Whenever we were talking about kinematics and all, we were talking about pure translational motion, right? So it is nothing new to you. Whatever you have studied till now was pure translational motion. Now what we are trying to do is we are actually comparing translational motion with rotational motion, and we are making some new formulas. So if you are going to look over here, I have got this formula. Like kinetic energy for rotational motion can be written as half omega square, and then I have got something in bracket, right? I've got something in bracket, and by the way, that thing is m1 r1 square plus m2 r2 square and so on, mn rn square. This is formula coming out to be. Now I want you to actually compare this with kinetic energy of translational motion. That was half mass times v square. So for rotational motion, instead of v, I have written omega. That's completely understandable, right? Now instead of mass, the role which mass played in translational motion, I have got something else written over here. I've got over here is m1 r1 square plus m2 r2 square plus and so on. So now we are going to actually name this thing as, and you know what are we going to call this? We are going to call this thing as moment of inertia of that rigid body. The rigid body that we were discussing about. All right. So we have got a new term, and that's what our topic is now. We are going to actually talk about now we are going to actually discuss moment of inertia, then the combined rotational and translational motion. We'll deal it when we are going to start rolling. Although it's nothing. All you need to understand is that right over here we have got a fixed axis of rotation. Now if this axis of rotation starts moving, right, then that is going to be called as a rolling motion. So you have got particles which are rotating about this axis, and now if this starts to move, this is going to be a translational plus rotational motion. So we are going to deal with that later on, so nothing to worry about. Now let's move to moment of inertia. Till now I have already explained it to you that okay, moment of inertia is nothing but it is actually analogous to mass from translational motion. What I mean is the role which mass played in translational motion, same role is going to be played by now moment of inertia when we are going to talk about rotational motion. So let's go a little back. What role did mass played? Mass was nothing but basically by mass we understood what inertia is, right? So if you have got a heavier object, if you have got a body which has got larger mass, we are going to say that it has got larger inertia, which means it has got a larger tendency to resist any change in its motion. Is it all good? Right? If we have got a body who has got a larger mass, it is really difficult to change the state of that body. If that body was moving, it's really difficult to stop that body. If that body is at rest, it is really difficult to move that body because of its larger mass. Of course, I am talking about in a relative sense. Let's suppose that we have got two bodies which has got one has got a smaller mass and one has got a larger mass, right? So in a similar way, moment of inertia gives a measurement of the resistance of a body to change in its rotational motion. This is the most important thing, that first of all it gives a measurement of the resistance of a body to change in its rotational motion, right? So now I'm not going to actually say that, okay, so if I've got a heavier object, it is difficult to actually bring a change in its rotational motion. Well, that statement is not incorrect. It is absolutely correct. A heavier object has got a heavier moment of inertia, but we are going to actually use our newly coined term, which is moment of inertia, because it is actually it will actually what we can say, it will contain all the necessary facts in it, right? So if you want to talk about the resistance offered to change in rotational motion of any object, we are going to call that quantity as moment of inertia, right? So now we are going to discuss moment of inertia of different particles, but before that, let's have a thought experiment, right? You know what thought experiment is? Thought experiment is, we don't really require any physical objects to perform this experiment. I just want you to think about it, right? I just want you to think. So let's suppose you have got a long rope. You have got two ropes with you, right? You have got two ropes, and one of the rope is of length 1 meter, and you're holding this rope from this point, right? So this is where the axis of rotation is going to be. I'm considering this to be the plane of the motion. Please try to understand. So axis of rotation will be something like this, which means this, and at the other end we have actually tied a stone over here, a stone of mass m, right? So the axis of rotation is something like this. All right. Now what I am trying to say is, we have got the same object, but now, and so you are actually trying to swing this stone of mass m tied to a rope. You are holding the rope from this point. You are trying to actually rotate it. Now you have got the same body, same mass, but now instead of 1 meter of length, you have got 5 meter of length. So over here this length was of 1 meter, and now over here this length is now of 5 meters, and same mass you have got. Let's say this is, so m. Now think about it. You do, I mean, you can obviously you can you can actually do this experiment, but I just want you to think about it. In which case you will feel, in which case there will be more difficulty to put that stone into rotational motion? Obviously in the second case. What's the reason? We have specifically taken that the mass of both the object is same. I mean, if let's suppose in the other case, I would have said that, okay, I've taken the same length of the rope, and I've taken, instead of like m, I have taken 10 times of m. Obviously you would have said, okay sir, it is now quite easy. If I have got a larger mass, this body, it will be more difficult for me to put this body into rotational motion. So this system has got larger moment of inertia, or this body has got larger moment of inertia, right? So that was actually quite logical. So one thing is very easy, that yes, moment of inertia does depends upon the mass. That's absolutely correct. But what really happens over here? We have got same mass m, but now the length of the rope has been increased to 5 times. Can you really imagine that it will be really difficult to put this body into motion? You will actually have to apply a lots of torque to make this body into rotational motion. So what's the other thing? The other thing is, actually, instead of just talking about the mass, let's now say that moment of inertia actually depends upon depends depends upon the distribution of mass. So this will contain each and every fact. So when we are saying distribution of mass, we are talking about mass, and we are talking about at what distance the mass is kept from the axis of rotation. And we are going to again and again we are going to talk about this thing, but please try to understand this is actually quite important for us. So make a note of it, that it depends on the distribution of mass. So you can also say I mean, can we expand this point a little bit? Yes, we can expand it. We can say that, okay, so moment of inertia actually depends upon, instead of talking about just mass, let's say it depends upon the density of the body. It depends on the axis of rotation. It depends upon the shape and size. And when we are going to talk about moment of inertia of different bodies, I'm going to again and again come back to to these facts, right? So this is very important. Moment of inertia of body depends upon the density of the material, shape and size of the body, and axis. When I say axis of rotation, if you're going to change the axis of rotation, and when I say changing the axis of rotation, which means that the mass distribution, if the mass distribution has changed, the moment of inertia of the body will get changed, right? Now moving on, let's talk about moment of inertia of a single particle. Do you remember when we were talking about rotational motion, we discussed that moment of inertia of a single particle will be written as, first let me draw, let's suppose this is an axis of rotation and I've got a single particle. I've got a single particle at a distance of r from this axis, and it has got mass m. Right? So the moment of inertia of this body will be written as m times r square. Quite easy. Right? So this is for a single particle. Now let's suppose if you have got like multiple particles, if you have got like system of particles. So if you have got system of particles, which means that instead of having only one particle, we have got n number of particles. So let's suppose we have got m1 over here at r1 separation. We have got m2 at r2. We have got m3 at r3, and let's say we have got n number of such particles. We have got the last one, nth particle at rn, right? So the moment of inertia of all of these things is nothing but the sum of moment of inertia of individual particles. So I'm going to write it in one line. Moment of inertia of this system will be the summation of, or first let me write it as okay. So let me write it as m1 r1 square plus m2 r2 square and so on plus mn rn square. Now please try to understand, this is what we did when we were talking about center of mass of individual particles, right? So this is going to be, I'll use a summation sign, mi rn whole square, and I is from 1 to n. That's it, right? So hopefully you have got it. Now let's do one or two questions regarding this, just so that you all feel a little bit more comfortable about moment of inertia of system of particles. Then we will move to moment of inertia of bodies which has got continuous mass distribution. So let's write the moment of inertia of this system of particle. This is actually system of two particles, and let's write the moment of inertia about different axes. Let's first write the moment of inertia about AB axis AB. Let's write the moment of inertia of this system about CD, right? So if you are going to write about AB, the moment of inertia will be written as m1 times r1 square. You don't have to worry about whether the particle is towards towards this side or the other side. You don't have to worry about that. Plus m2 times r2 whole square, right? For moment of inertia about CD is going to be, what is going to be the moment of inertia of m1? So we are going to write m1 times square of 0 plus m2 times, now the distance of m2 from CD is actually r1 plus r2. So I'm going to write r1 plus r2 square of this, right? So now you can also find out the moment of inertia about an axis passing through m2. You can do all of those things. Moving on to the next one. Three light rods each of length 2L are joined together to form a triangle. Three particles A, B, C of masses m, 2m and 3m are fixed to the vertices of the triangle. Find the moment of inertia of the resulting body about an axis through A perpendicular to the plane of ABC. Alright. So we have got, and please, if you want, please pause the video, do it by yourself. So we have got three rods and they have got equal length of 2L. And then we have got three particles m, 2m and 3m. So these are basically particles A, B and C, right? Find the moment of inertia. Alright, an axis passing through A. So the first thing is an axis which is passing through A. Let's suppose that this is A. Obviously I have assumed this to be A. This is A, B and C. Alright, so if you want to find out the moment of inertia about axis passing through A, then we are going to write it as, there will be no moment of inertia because of this particle. So m times square of 0 plus 2m times square of 2l plus 3m times square of 2l, right? So this is actually 4l square and we have got 5m. So we have got over here as 5m times 4l square, which is nothing but 20 ml square. So 20 ml square. Now the next thing was an axis passing through A and the midpoint of BC. All right, passing through A and a midpoint of BC means this is your axis of rotation. Now first, this is your axis of rotation. Alright, so again there will be no moment of inertia of A with respect to this axis, right? This is going to be 2m L square, 3m L square. So moment of inertia, let me name this axis as x dash. So this is actually 2m plus 3m into L square. This is 5m L square. So the correct answer is going to be option A. Hopefully you have got it. These questions are quite easy, but yeah, good for our starters, right? So that's all you are going to see from moment of inertia from system of particles. That's it, right? So let me see if you have got any more things. No, now we are going to start with the next topic, which is actually moment of inertia of a rigid body. So moving on, now we have got moment of inertia of a rigid body, right? So now let's suppose that we have got an axis of rotation, something like this, and before drawing an axis of rotation, let's draw a rigid body. Let's say we have got a rigid body of total mass m and an axis of rotation passing through something like this. Now we have to find out the moment of inertia of this body. So let's suppose that we have got an element over here of mass, of small mass dm, kept at a distance of, let's suppose, x. So the moment of inertia of this infinitely small particle can be written as di. So di would be written as, the separation is x from the axis of rotation times dm. Right. So if I want to find out the moment of inertia of this entire rigid body, then what I can do is I can actually use the integration of sign, is the sign of integration, and I can say, I can rewrite this thing as x square times dm. So instead of summation, now we are going to use integration, and same thing. So see, now again I am going to say that we are about to start. I mean, by the time you are going to watch this video on YouTube, it's already going to be, it's going to be 1st of January, or right. So now you only have got 3 or 4 months. Now you really can't say that, okay, I'm going to start practicing each and every derivations. You don't have that much amount of time, but still you can focus on particular derivations, then you can quickly move on, right? So still you have got time for doing some of the derivations. What you can, I mean, how you can do all of these work smartly is, the derivations that we did in center of mass, everything is quite similar to what we are going to do over here as well, right? So now the first derivation is of moment of inertia of uniform rod about a perpendicular bisector. Now please understand, when I say a rod, I mean to say that mass is distributed along only one dimension, right? So let's suppose that we have got a rod of length L and perpendicular, let's suppose this is the perpendicular bisector, this is your axis of rotation. So if this is the axis of rotation, again we are going to do the same thing. Let's suppose that we are drawing an element over here at a distance x. So this element is of mass dm and it is at a separation of x from here, at a distance of x from here, right? So again I'm going to rewrite the same thing. The moment of inertia of this small mass is going to be di equals to x square times dm. If you remember from the center of mass, what is the problem over here? The problem is that, okay, x is the variable and we are trying to integrate x with respect to m, which is not possible. So we must convert one of them. So let's suppose that lambda is the linear mass density of this rod. So if lambda is equals to m by L, then it will also be equals to dm by dx. And by the way, what is dx? Dx is the length of this infinitely small, what you can say, strip. This is dx, right? So instead of dm, I can rewrite that as m by L times dx. So problem solved. Same thing we have done in center of mass also. So now let's substitute the values. So I'm going to again rewrite this thing as di equals to x square. I don't have any problem with x times dm. So dm is going to be m by L times dx. Now after this, please understand what limit are we going to put. So if this is the perpendicular bisector and the total length is L, so I would assume that, okay, this is the origin, so this is x equals to 0. So I can write this thing as x equals to minus L by 2 and this thing to be x equals to L plus L by 2. I must use signs to represent, to to explain that okay, this is the perpendicular bisector and half of the rod is towards the left of this axis and half is towards the right of this axis. So now after integrating it, I'll get the moment of inertia of this system, and the limits are going to be minus L by 2 to L by 2. So let's quickly solve it. So we are going to get M, L, and this is actually going to be x cube by 3 minus L by 2, and this is going to be L by 2. This is M by L, and this is going to be L cube. And please understand that this thing is actually this thing is 3 and this is going to get cube, so this is your 8, right? So this is going to be 24. Then we'll put a minus and minus, we'll get plus, so this is again L cube by 24. So the final answer that we are going to get is ml square by 12. So please remember the answer. So the moment of inertia of the rod about the perpendicular axis, see, this is the important point, that it's just not that you will remember the moment of inertia and you will be good. You must remember the moment of inertia about a particular axis, right? I mean, they both will go with the same line. You can't just remember, okay, moment of inertia of rod is ml square by 12. Obviously that is not true, right? So moment of inertia of a uniform rod about perpendicular bisector is ml square by 12. So this is going to be ml square by 12. And then what you can now do is, if you think that you can actually find some time for doing this derivation still at the start of January, right? If you think that okay sir, I have got some time, I can do a little bit of practice. So what you can do is please derive it for this axis, for an axis passing through from this edge, just for practice, right? Although we are going to do it using theorem of parallel axis, we are going to do it, but still if you want to do it. So now let's quickly move to the next next derivation. We'll do couple of derivations, then we'll move on to some new topics, right? Because then you'll get an idea. Now let's suppose we have got a rectangular plate, and this rectangular plate has got certain mass, okay, and let's suppose the dimensions that we have got over here are, this is L and let's suppose this is B. About a line parallel to H. So about a line parallel to H means, and they have not said it, but the thing is, it is something like this. The axis is something like this. It is passing through the center and parallel to H, right? So I'll add one thing, and it is passing through the center. All right. So this is our axis of rotation, my friends. Let's do the same thing. What is the first concept, my dear friends? The first concept is to cut an element. What do you mean by element? Do you remember we discussed the same thing in center of mass? Let's suppose that we have got a thin strip over here. Let's suppose we have got a rod of mass dm, and it is at a distance of, let's say this is at a distance of x from here, and the thickness is dx. So this is x and this is dx. I've written each and everything over here. Again, we are going to write the same thing. We are going to write, okay, the small moment of inertia due to this thin strip is going to be mass times distance, which is I have written as x square. Fine. Hopefully everything is clear. Now I have to convert this dm. So for converting this dm, I'm going to say that let's suppose that the surface mass density of this thing is m upon lb. Is that correct? Mass per unit area equals to the mass of this strip, that is dm, divided by what is the mass of this strip. So mass of this strip is actually, the length is the width is b times dx, right? Width is dx times b. So b times dx, obviously b can be cancelled out, and instead of dm I can rewrite this thing as m by l times dx. So now let's rewrite the formula of di. Di will be x square times m by l times dx, and now let's integrate it from x equals to, this is going to be minus l by 2 and this is going to be plus l by 2. So derivation is, integration is exactly same. You have got x square ml dx, right? Exactly same. So the answer is going to be just ml square by 12. Can I simply write it like this? Right? So this is the moment of inertia about this axis. If someone asks you that what is the moment of inertia about this axis, now can we simply write it? So we are going to say, okay, if we want to find out the moment of inertia about this axis, it is going to be, I'll call it as I dash, it would be m b square by 12. So you need to remember all of these things, right? Hopefully everything is clear till this point. Now let's move on and let's move to some new, let's suppose that you have got a ring, all right? We have to find out the moment of inertia of a ring. What would be the moment of inertia of a ring? Think about it. Obviously, first you will ask me, sir, please tell us about which axis you are asking it. So about an axis passing through its center and perpendicular to the plane, right? So something like this, about an axis passing through the center and perpendicular to the plane, right? And the usual things, that means it has got mass m and radius r. So you are going to say, okay, it's fine. So moment of inertia of any small part will be written as, similarly it will be written as di dm times r square. Is that correct? Now the easy part over here is that each mass, the dm that you have considered, each of these dms are at the same separation, are at the same distance from the axis of rotation, which is actually nothing but r. Is that correct? So the total moment of inertia is going to be nothing but mr square. Is it correct? What about a circular plate? Pause the video, derive it for a circular plate. And even before deriving it, I mean, if you remember the formula, good for you, but before deriving it, first tell me, if I've got the same mass as m, that means now I've got a circular plate of mass m, right, of equal radius. The only difference is now that it has got mass inside, mass on the surface, right? So it has got, this one has, and the axis is also, by the way, same. I'm just drawing some axis over here so that I can draw a center. So the axis of rotation is again this, an axis passing through the center and and perpendicular to the plane. So you tell me whether the moment of inertia of ring is going to be, moment of inertia of ring is going to be greater than the disk or the other way around, or are they going to be equal, right? Think about it. Before deriving it, think about it. What should be the case? You have now understood the definition of moment of inertia. We discussed the dependency of moment of inertia on certain factors, right? So thinking about those factors, tell me without deriving it whether the moment of inertia of disk is going to be greater than that of a ring or not. Pause the video, think about it. Hopefully you have tried it, right? So now how we are going to actually do it? First, let's cut two circles, two concentric circles, something like this. Two concentric circles, something like this, right? That means a ring. It is nothing but obviously it is a ring which has got mass like this, and by the way, this has got a thickness of dx, radius of x, mass dm. Is that all good, right? So that I can write mass upon area. Area of this circular plate is going to be nothing but pi r square. That would be equals to mass of this circular ring having infinitely small thickness divided by the area of this thing. So area of this thing is going to be 2 pi x times dx, right? So I can cancel out this pi. So dm is going to be 2x dx m upon r square. So this is your dm, right, that we usually need. Now the next thing is going to be rewriting di. So di will be x square, and instead of dm I'm going to rewrite it again 2x times dx divided by r square times m, and now I'm going to actually integrate it from 0 to x. So this is actually, I've got m upon r square as constant. This is, and also 2m upon r square, and the integration of x square is going to be, sorry, this is, I've got x cube, so it is going to be x raised to the power 4 upon 4, and the limits are going to be from 0 to r. Now please look, this thing can be written as 2m upon r square, and this will be written as r raised to the power 4 upon 4. So this will be r square and this will be 2. So this will come out to be mr square by 2, which means half of the ring. So for a disk, for a ring, you have got mr square, this r stands for ring, and for a disk, the moment of inertia is mr square by 2. Doesn't it explain whatever we have studied about the moment of inertia, the dependency of moment of inertia? Moment of inertia depends upon the distribution of mass. Now, when you are going to compare the distribution of mass for a ring and a disk, the mass in a disk is actually closer to the axis of rotation. So it is easier to change the state of rotational motion for a disk as compared to that for a ring, obviously of same radius and having same mass, right? We are comparing apples with apples, right? So same mass m, same radius r. moment of inertia is going to be mr square, moment of inertia is going to be mr square by 2. Now I hope that you can, if someone asks you for a hollow cylinder, so if we are going to discuss for a hollow cylinder, again same thing, again we are going to land to the same conclusion, that for a hollow cylinder we have got something like this. The mass is only at the periphery, that means only at the circumference, so we don't have to worry about, and we'll simply say that the moment of inertia of a hollow cylinder is again going to be just mr square. When you are going to talk about a solid cylinder, then you are going to consider that solid cylinder is made up of hollow cylinder having thickness dx. So now I hope that you can derive that thing, right? So please remember some of the formulas for this, like for rod about perpendicular bisector is ml square by 12. Plane for a plate about line parallel to edge passing through its center is mb square by 12, where b is going to be the length of the side, length of the side of the of the other side, not for the parallel one, right? Then we have got circular ring, which is mr square, circular disc mr square by 2, hollow cylinder mr square, solid cylinder is going to be mr square by 2. Obviously we must write two more formulas, which is for moment of inertia for solid sphere, which is 2 by 3 mr square, right? And now again please tell me, moment of inertia of hollow hemisphere will be greater than this or smaller than this? Obviously greater than this, it is hollow, right? So moment of inertia, sorry, this is actually 2 by 5, solid is 2 by 5 and hollow is 2 by 3. Hollow sphere is 2 by 3 mr square. So now let's move to our theorem, which is theorem of parallel axis, right? So theorem of parallel axis is actually quite it is quite useful. Please don't consider this theorem as a part of your school syllabus only, because you can actually use this theorem to solve many numericals, right? We'll look into it. The theorem basically says, let's suppose that you have got a rigid body and the moment of inertia of this rigid body with respect to this axis, let's suppose with respect to this axis is I1, and this is known. Moment of inertia about this axis is I1. And we have got another axis which is parallel to the former one, which is somewhere over here. And this is, let's say this is I2. And the separation between these two axes is D. These two parallel axes is D. And mass of this rigid body is M. Right? So what I'm going to say, what the theorem of parallel axis state is I2 can be written as I1, which is moment of inertia of the rigid body about the known axis, plus mass of the body times square of the separation between the two axes. Simple thing, right? We can have an example of this as well. Let's suppose that you have got a rod, and we already know that the moment of inertia about the perpendicular axis is, perpendicular bisector is ml square by 12. Now let's suppose you want to find out the moment of inertia about this axis. how you are going to name it? About an axis which is passing through one of its edge. So it is going to be moment of inertia about the perpendicular bisector plus mass of the rigid body times square of the separation between these two. So this has to be L by 2. So this is going to be L square by 4. Is it correct? Right? So this will come out to be ml square by 3. So you can use this application, you can use this theorem anywhere you want, right? So let's see if you have got a question like this. We have got 3 rods, each of mass m and length L are joined together to form an equilateral triangle. Find the moment of inertia of the system about an axis passing through its center of mass and perpendicular to the plane of the triangle. Now see, obviously they have not said that use a particular theorem for this, but how we are going to know that we must use this theorem. So now the question is, we have got 3 rods, each of mass m and length L, right? And the center must be somewhere over here. And this is an equilateral triangle. So if this is an equilateral triangle, we know that this angle is going to be 630 degree. And this is going to be L by 2. Can I find what this length is? This is, let's say this is X. I'm talking about only one rod right now. Let's suppose we are just discussing about this rod. So this rod has got mass M. They have said that this rod has got mass M and this has got length L, right? And we know that what is the moment of inertia about this axis? Please try to understand. We know that moment of inertia about this axis is actually ml square by 12. You are going to say, sir, that axis was something like this. This is the rod and this is the axis. I mean, no worries, dosto. If this is the rod, moment of inertia about this axis is also going to be ml square by 12, isn't it? This is also perpendicular bisector. So this is ml square by 2. And we need to find out the moment of inertia about this axis, which is passing through the center and perpendicular to the plane of this triangle made by these 3 rods. So let's find out the moment of inertia of this single rod about this axis, then we'll multiply it by 3, right? Because everything is symmetrical. So to find out what this x is, we'll simply use the very simple trick. No, tan 30 degree is going to be equals to 1 over root 3, and that will be equals to x divided by L by 2. Is it correct? So x comes out to be L upon 2 root 3. So let's apply the moment of inertia. So moment of inertia about the center, that centroid point equals to 3 times. Now you know why I'm multiplying 3, right? 3 times of moment of inertia due to a single rod, and that is actually equals to ml square by 12 plus m and the square of the distance. So this is going to be L square by 4 times 3, which is again going to be 12. So this is going to be 3 times of ml square by 6, which is going to be ml square by 2. So please let's quickly check this, check the solution, and I think if that's all good, this is going to be ml square by 2, right? So please have a quick look on this. So now let's move on to, okay, let's have one more question. Find the moment of inertia of a solid sphere. So solid sphere basically means that moment of inertia is going to be 2 by 5 mr square. About this axis x dash, right? That's what they mean, I think. So what we are going to do now is, we know that moment of inertia passing through the center passing through the center is going to be or wait a second. We'll actually do this after doing what we after doing moment or after doing perpendicular axis, right? Although you can solve it using parallel axis also. No, this is actually a sphere. So the moment of inertia about this is 2 by 5 mr square. So this separation is r. This is going to be just 2 by 5 mr square plus mr square. That's it. So which means 7 by 5 mr square. So now let's move to theorem of perpendicular axis, and before actually going through the definition of the statement of perpendicular axis, let me explain it to you. First of all, theorem of perpendicular axis is only for planar bodies. That means lamina, two dimensionals. This is a point to be noted, right? And what does it states? It states that let's suppose that we have got a rigid body, a laminar body, and we want to find out the moment of inertia about an axis which is perpendicular to the plane of this body. So let's suppose this is an axis which is perpendicular to the plane we want to find out the moment of inertia about this axis, right? And we know the moment of inertia about two axes which is in the plane of the body. So let's suppose that this is x-axis, this is y-axis, this is the point of intersection, right? So the moment of inertia about the z-axis, this is your, let's suppose this is the z-axis, is going to be the sum of moment of inertia about x-axis and y-axis. So this is the theorem. So two things are very important. First of all, this is applicable only for two-dimensional bodies, right? The next thing is the moment of inertia about an axis which we want to find out, right, should be perpendicular. So this axis, it should be perpendicular to the plane of body, right? And x and y should be perpendicular to each other as well. So now if we have got this part, then let's find out the moment of inertia of a uniform ring. So we have got a uniform ring, something like this, about a diameter. Now please understand, we know the moment of inertia of this ring about this axis passing through its center, right? So about the diameter is, let's consider we have got two diameters, one like this and the another one like this, right? So I'm going to say the moment of inertia about the axis, about the z axis, is equals to moment of inertia about x axis plus moment of inertia about y axis. Now please look, moment of inertia about x axis and y axis are going to be same, because they both are basically diameters. These are nothing but these are diameters, right? So 2 times of moment of inertia about the diameter is equals to I z z dash. So moment of inertia about diameter is going to be, this was mr square, so this is going to be mr square by 2. This is your answer. All right. Now let's move to next question. I can actually give you one or couple of questions in homework as well. So two rods each having length L and mass M joined together at point B, alright, as shown in the figure. Then find out the moment of inertia about an axis passing through A perpendicular to the plane. Okay, so we have to find out the moment of inertia about this axis, right? So of this whole thing, of right. So you can actually use again theorem of parallel axis over here. Why theorem of parallel axis? I will tell you. First of all, we know that the moment of inertia of this rod about this axis, this is going to be I equals to ml square by 12, right? This is ml square by 12. And I know that moment of inertia of this AB rod about this axis is nothing but ml square by 3. So you just have to find out the distance between these two axes, and you can use it, you can find it using Pythagoras, right? You just find out this and then just add all of these moment of inertia. That's it. So quickly do this in homework and write down the answer in the comment section. This is for slide number 28. This one is for your homework. All right, moving on to the next topic is torque. Now we started this chapter and I told you that we are going to again and again compare rotational motion with linear motion, right? So we have coined a new term, that is moment of inertia, analogous to what mass was in kinematics, right? In pure translational motion. Now we are going to again talk about a thing that is known as torque. So torque is nothing but it is an ability to change the rotational motion, of the body. All right, so let's suppose that you have got a rigid body over here. You have got a body, and let's first consider that I'm talking about a point on a Cartesian plane. Let's say this is the point we are talking about, and we want to find out the torque about the origin. So we have to find torque about origin. And let's suppose the force that is acting on this point is F, something like this. So this is known as point of application of force, right? And let's suppose that the angle, that this angle is theta, and this position vector is r. So the torque about point O will be written as r cross F. That means we are going to talk about the vector product of position vector and force vector, right? And the magnitude of torque about origin will be written as Rf sine theta or R perpendicular times F or R times F perpendicular. Hopefully every one of you know how to find out the direction of torque, right? Any cross product can be determined by our simple right hand rule. So for this one, the right hand rule is going to be R. Place your fingers along the direction of R. Move your fingers in the direction along the direction of acute angle R cross F. Thumb is pointing inside. That's what the torque is in this direction, in this particular case, right? So that is cross, that means into the plane or in clockwise direction, right? Now after learning about the torque, let's have a numerical over here. And by the way, we have got one notation that is missing from this point. This is also 4 centimeter. Now please again pause the video, solve this question. You have to find out the total torque about point O, right? First of all, torque due to this force will be 0. Because this the point of application and the point about which we have to find the torque is same, so this is going to be 0. Now quickly find it out along with the direction. See how we can do it. First let's talk about this 10 Newton. So the net torque will be, this is 10 Newton times, you don't have to worry about the perpendicular distance. This is the perpendicular distance because they have already told us this is 90 degree. So 10 times 4, direction is very important. So to quickly find out the direction, R cross F. So this is inside, so I am considering inside to be positive, right? So cross to be positive and dot to be negative. You can do opposite of this as well, right? Now the next thing is, after this, if you are going to talk about this 20 Newton, right? This is 150 degree. This means that I can actually I can translate this force over here as well. So this was 20 Newton. This is 150 degree. That means this is 30 degree. Is it correct? So that means if I'll draw a perpendicular force, that is going to be 20 sine 30 degree, which is going to be 10 Newton. So this is going to be, are you getting it quickly? R cross F, right? So 10 cross 4. So I'm going to use a minus sign, 10 cross 4. So they both are getting cancelled out, right? I don't have to worry about this one. Similar thing over here, I'll transpose this vector on this side. So this is 15. So this is going to be 15 sine 37, which is 3 by 5, right? So this is going to be 9. So that is coming out to be minus 9 times 6. Please have a look. I think everything is clear. So this gets cancelled out and I'm getting my answer as minus 54. And if I look at the unit, it is Newton centimeter. And if I'll convert it into Newton meter, it's going to be minus 0.4 Newton meter, which is going to be option number B. Please have a look. And negative or positive sign doesn't make difference over here. Negative sign basically means that the net torque is in the outward direction. All right, so now let's move on. Now, since we have completed about torque, now let's again discuss about equilibrium. If you remember, we did equilibrium in work power energy, and when we were talking about equilibrium, then also I told you, whenever we are going to say that a body is in equilibrium or a system is in equilibrium, it means that this single word means that that particular body or that particular system will experience no net force, that means the net force is going to be 0. Also the net torque is going to be 0. Right? So we are going to actually use couple of we are going to use this concepts in couple of questions, something like this. Let's suppose you have got a question over here, and this says determine the point of application of a third force for which the body is in equilibrium when the forces are 20 and 30 Newton, something like this, right? So we have got 30 Newton over here, 20 Newton over here, and they are saying that such that this is in equilibrium. So if it is in equilibrium, if this thing is in equilibrium, the first step is that the net force will be 0. So if net force is 0, if you have got 30 Newton in downward direction, definitely we must write a force in upward direction. And let me just draw it. I really don't know whether this force, where this force is going to be, but one thing is sure, this is going to be 10 Newton, right? Now the next step is writing the net torque. Net torque should be also 0. About which point? About every point, right? About every point. So let's just consider that, let's say that we are taking the net torque about point C. So this should be also equals to 0. So net torque about point C, at C we have got 20 Newton, so there will be no torque because of this 20 Newton. Because of this 30 Newton, it's going to be 30 times 20 and then minus 10 times x equals to 0. So x comes out to be 6 centimeter. So 6 centimeter from C. So if this is 6, hopefully everything is clear. It's 60 centimeter, sorry. 60 centimeter from C. That means if we are going to talk about from A, it's going to be 70 centimeter. So 10 Newton and 70 centimeter from A. So option B is absolutely correct. Right? So easy questions regarding these things. The next thing that you must try to understand is, we have talked about what about torque, right? How to write torque. The formula for torque is F cross R. Sorry, R cross F. This is the formula. And this is nothing but this is relation between the rotational force and the linear force. Is that correct? If again I'll ask you to compare the force, compare the torque with force, do you remember what force was? Force was mass times acceleration. So instead of torque, can I write moment of inertia times angular acceleration? Isn't it? Is that correct? Also, you can rewrite this thing as alpha can be written as summation of all the torques. That means the net torque divided by the moment of inertia of the rigid body. And this is only applicable for rigid body. Because if we don't have a rigid body like a let's suppose like a tank which is filled with water and it is rotating, right? A rotating tank of water. So in that case, we can't consider that to be a rigid body. So this formula we won't be able to apply this formula over there. So this is nothing but net external torque divided by moment of inertia. Right? So some of the relations you must actually try to understand. Another thing, if you will ask me to rewrite this thing, this force as the second law, I'll rewrite this thing as rate of change in linear momentum. So let's derive another thing over here, that is angular momentum, right? So let's derive a formula for this. Let's suppose that you have got Cartesian plane over here, and at position vector r, we have got a mass moving with some velocity, something like this. So we have got body of mass m with velocity v, and this angle is theta, right? So angular momentum, by the way, sorry, over here I should have written it as p. The angular momentum will be written as r cross p, or r p sine theta, or r p perpendicular, or m v sine theta. All right. So please note all of note these things as well. These things are also quite important for us. After this, if you want to find out, I mean, if you rewrite this formula, how we can actually rewrite it? We can also rewrite the angular momentum as moment of inertia times angular velocity. So this is also one of the formula, I times omega, right? So again, if you are going to talk about torque and all, you can actually again rewrite this thing as torque. We can rewrite this thing as torque equals to net external torque equals to the rate of change in angular momentum. Very important formula, because we are going to use it in conservation of angular momentum, right? Again, similar to what conservation of linear momentum is. Why I'm again and again rewriting those things that we have done in work per energy? Because it is quite similar, and it will also, I mean, you're going to revise the previous concepts as well. So conservation of angular momentum basically means, if let's suppose the net external torque is 0, right? If net external torque is 0, this would mean that dl by dt would be 0. And if dl by dt is 0, this means that the total angular momentum of the system will be constant. And now we can rewrite this thing in many ways. First is, this would mean that I times omega would be constant, right? So let's suppose there is a collision, there is collision between two particles, and we are considering that we can apply conservation of angular momentum. So in that particular case, we are going to rewrite things as I1 times omega 1 equals to I2 times omega 2. I'll explain it using an example. And when I have said collision, let's take two different examples. Let's say we have got a rod over here attached from a ceiling, right? And this is actually a hinge point, and a ball is coming of mass m, and let's say this has a mass capital M, and it is about to strike, right? Now please understand, when collision is going to take place over here, just before and after collision, hear me out, just before and after collision, there will be hinge force, and because of this hinge force, the net external torque will not be 0. Also, the net force will also not be 0. So there are two things. First is, you won't be able to apply the conservation of linear momentum, right? linear momentum is not conserved. Linear momentum is not conserved because of this simple fact. We have got a hinge force acting over here because this is a rod. Hinge force, you can consider it as a normal force applied by the support. Next thing is, what about angular momentum? Well, angular momentum is also not conserved everywhere. I mean, if you are going to talk about, sir, let's apply the conservation of angular momentum about this point, it will not be applicable. But if you are going to choose the hinge point, conservation of angular momentum about hinge point is valid. Why? Because if you are going to actually talk about the torque of hinge force at, let's say this point is H, at H, that will be 0, right? So you can apply conservation of angular momentum about the contact point. That is all good. Is that clear? And let's suppose that instead of having a rod, we have got a rope, then you don't have to worry about anything. If you have got a rope, then there is no hinge force, then everything is applicable. Conservation of linear momentum is also applicable, and conservation of angular momentum is also applicable everywhere. Valid everywhere. Similarly, we have got a, let's suppose we have got a mass m over here and another mass is coming to strike. This is the difference between a rod and a rope. So, I mean, now if you want to see how this is going to take place, let's take an example. A wheel of moment of inertia I and radius r is rotating about its axis at an angular speed omega naught. It picks up a stationary particle of mass m at its edge. Find the new speed. See, we don't have to actually draw the diagram also. We know that because we can see that, okay, even if it has picked up a new particle, still the net torque, the net external torque will be 0. So if net external torque is 0, we can say that angular momentum will be conserved. So I omega will be constant. So initially, and if this is constant, it means that I1 times omega 1 equals to I2 times omega 2. So I1 is moment of inertia of, they were talking about a wheel of moment of inertia of I, they have told us it is I. Angular speed is omega naught equals to, now the particle has sticked. So the moment of inertia of that particle is going to be m, have they told us mass, it is small m, into r square times omega. So omega will be equals to I omega naught divided by I plus mr square. This is going to be the final answer for this one. Moving on to the next one. Next question says a uniform rod of mass m and length L can rotate freely on a smooth horizontal plane about a vertical axis hinged at point H. Alright. A point mass having the same mass m coming with an initial speed u perpendicular to the rod strikes the rod inelastically. Inelastically means it will actually stick with it, right? Find out the angular velocity of the rod just after the collision. Please understand, we can apply the conservation of angular momentum over here, but the catch is we'll have to apply it about h, right? So the net torque about h will be 0. So before collision, the angular momentum was mul, right? Finally it would be, because it has now sticked with it, and we have to find out the angular velocity, right? So it would be moment of inertia of rod about this point. So that is going to be ml square by 3 plus moment of inertia of that particle about that point is going to be ml square times omega. I think this is going to be your answer. So we can cancel out this m, we can cancel out one of the l, right? So this is going to be u and this is going to be 4l by 3 times omega. So from here we can rewrite omega is 3u by 4l. Please have a look. I have used two types of formula over here. Over here I have used m into u into l, which was basically nothing but what you can say r cross p, and over here I have used I omega formula, right? And because over here I was given initial velocity, I have given velocity, and on the right hand side I want to find out what angular velocity should be, right, after the collision. Please have a look, then we'll move on. So now let's move on. Now let's talk about work and power in rotational motion. And see, again I'm going to tell you that on the right side of the board I'm going to give you a little revision of whatever we have done in work power energy, right? And similarly we are going to do the same thing for rotational motion as well. So if you remember, we had written work as a small work done as F time ds, right? And further force can be written as mass times acceleration, where acceleration can be written as nothing but dv by dt times ds. So this whole thing can be written as dv equals to m times ds by dt can be written as v times dv. So after integrating this, we got to the work energy theorem, isn't it? If we'll integrate it, we'll get work done equals to half mv square if the initial velocity is 0. So the work done is nothing but it is change in kinetic energy. This was your work energy theorem. So if you are going to do the similar steps over here, so for example, as dw can be now written as torque times d theta. Further, this can be written as I times d omega by dt times d theta. So finally, now you got the drill. Work done can be actually written as change in rotational kinetic energy. So this means we can rewrite this thing as half I omega 2 square minus omega 1 square. This is your work energy theorem, right? Applicable in rotational motion also. So after this, if we'll talk about rotational power basically means work done, rate at which work is done. This will be d theta by dt. So that means this is going to be power, and this will be your torque times omega. This is your formula for rotational power, right? So we have completed all of these things. Now let's complete the last portion, which is rolling motion. Please note that this is actually quite important. So I'm going to almost talk about each and everything. We are going to also discuss when a body rolls down an inclined plane, then what happens, friction. We are going to also include friction in it, right? So let's start. First of all, rolling motion basically means the combination of rotational motion plus translational motion, right? So let's suppose on a ground, we have got a body which is rotating about this axis, right? It is rotating about this axis with, let's say, angular velocity omega. So this is the axis of rotation, and this axis is moving with a velocity, with a linear velocity of v. This is what do we call as a rolling motion. When we have got combination of rotation plus translational motion, right? So if we want to find out each thing over here, like for example, as we want to find out the velocity of each point, let's start with this point. So this point has got a velocity in forward direction because of translational motion. See, this is nothing but this is the combination of two things. So this would mean I'm going to actually rewrite this thing as one is completely translational motion and the another one is rotational motion. So for translational motion, each particle, no matter where that particle is, each particle of that body will move with the same velocity, and that will be v. So each one of them will move with v velocity. This is in accordance with the definition of pure translational motion. If you are going to talk about pure rotational motion, each particle will have a velocity of r omega, something like this. All right. So if we have to draw a combined motion, so combined motion will be drawn something like this. So if you want to draw the velocity of this point, first we are going to talk about v over here, which is because of translational motion. Then we are going to talk about r omega over here. If you want to draw the velocity of this point, we are going to draw it something like this. So this is going to be v plus r omega, right? If you want to draw the velocity of this point, then this is going to be v and this is going to be r omega. So if you want to find out the speed at any point, just find out the resultant of these two vectors. So this is going to be square root of v square plus r omega square. Is that correct? Right? So we can find out speed at any given point. So now the thing is, in rolling motion, we have got two types of rolling motion. One is pure rolling motion, the another one is impure rolling motion, right? Now, what do we really mean by these two things? Let's suppose we are saying that a body is in rolling motion and in such a way let me draw it. This is in rolling motion. And by the way, this is the same body, right? Let's suppose this is point A. What I am trying to say is this body is also rotating as well as it is translating into this direction. What I want to say is when this point will complete one rotation, when this point will come back to over here, then let's say it has transferred certain distance. Are you getting it? So after a certain period of time, point A will be over here, it has gone to this, then this, then this, and then finally this point will complete one rotation over here. Is that correct? So if let's say this distance is equals to 2 pi r, let's suppose this is s. If s is equals to 2 pi r, and of course r is the radius, then we are going to say this is the case for pure rolling, and the condition for pure rolling is V equals to R omega. This is the important condition. V equals to R omega. Alright. Now we can actually rewrite this thing in many ways. What does it mean? If this is V equals to R omega, it means that the net velocity over here, we have got V, and in backward direction we have got V, we have got R omega, which is also equals to V. So that means the net velocity of this point is going to be 0. What does it mean? It means that there is no relative motion. This point basically means there is no relative motion between contact point and ground. Are you getting it? Right? There is no relative motion. So even if there was friction, and if this was a rough surface, then also if this is the condition, no friction is required. Please try to understand, no friction will be applied by the surface, or no friction will be there between the surfaces. Why? Because there is no point of contact, there is no relative motion between the point of contact. Right? This is the most important thing about the pure rolling, that first the S will be equals to 2 pi r. Second is condition is V equals to R omega. So this is a very important condition. Condition for pure rolling. And after this we can also rewrite this acceleration as R alpha. This thing is also applicable. All right. Let's talk about the another cases. Let's suppose that S is greater than 2 pi r. So this is the case for forward slipping. And if S is less than 2 pi r, then this is the case for backward slipping. All right. We are going to come back to forward slipping and backward slipping. First, let's discuss what is going to be the speed at different points. We have already talked about this. S is going to be 2 pi r, right, for pure slipping. Now let's say we want to find out the speed at any point. Speed at any point on circumference. And let's suppose we are talking about for pure rolling. Because we want to take a general point, let's suppose that we are taking a general point somewhere over here. All right. So this is the point that we are talking about. This is the point. We want to find out the speed of the particle at this point for pure rolling. So pure rolling basically means, whenever you are going to talk about pure rolling, it means one thing, that V is equals to R omega. right? Okay. Also, rolling basically means that we are talking about one velocity, something like this, which is actually equals to nothing, but this is actually equals to v, right? And this is the linear velocity because of rotational motion, which is actually equals to r omega, which in this case is also equals to v. Hopefully everything is clear till here. Let's say that this angle is theta. Everything's clear? If this angle is theta, let's break down the component of this v. So this is going to be, see, let's quickly, we are going to break down two components. So see, this is theta, right? So this is theta, then this is theta. So this is going to be theta. So this is going to be v cos theta. Instead of writing r omega, I am writing v cos theta. And also please try to understand, instead of theta also I can write it as omega t. I mean, this is nothing but what I am trying to say is, let's suppose at this point we have t was equals to 0, and after t time we are trying to find out the speed, right? So the net speed at that point will be the vector sum of v minus v cos theta. That means this can be written as 1 minus cos theta. I can eat a lot of time over here by writing all the trigonometric formulas, but you know this thing can be instantly written as v times, this thing can be actually written as sine theta by 2, right? Sine square theta by 2. So further we can rewrite, instead of v, we can write it as r omega sine square omega t by 2. So this is the speed at any point. If you know time, you can find out the speed. So I mean, instead of solving numericals, I have already derived this formula for all of you. Now you can actually, you can just substitute the value and you can just find out this thing, right? Hopefully everything is clear till this point. By the way, sorry, one thing over here, we have to actually, sorry. We have to, this has to be done in this way. This is all good. We have two velocities which are v and v cos theta. See, I have done one mistake over here. This is actually not v net. This is v net along x axis, right? This is actually along x axis, and we have got along y axis as v sine theta. So this is actually vy is actually equals to v sine theta, and the vector sum of these two is going to be the resultant. So quickly let's do it. So v net, that is the speed, is going to be the vector sum of v sine theta plus square of this plus v square 1 minus cos theta and square of this as well, right? We can take out this v common, and this thing is sine square theta plus this thing is going to be cos square theta minus 2 cos theta. Further we are going to write v under root of, we have got 2 and 2 over here, so I'll write 2 1 plus 1 minus cos theta, right? So this thing will become 2v sine theta by 2. So this thing can be written as 2r omega sine omega t by 2. So this is the speed at any point. Please remember this formula. So speed at any point is 2r omega sine omega t by 2. So this is the formula. Now if you actually want to find out the, see, I mean, I have told you that after some time this point A will be somewhere over here, right? Then after some time that A point will be over here, then A point will be over here, and then finally it will come back. So the path of this thing, this path is actually known as a cycloid path. you want to find out the length of this cycloid path, this comes out to be 8r. Now again, these things are not like extremely well, these things are important for NEET as well, but you can actually move on by remembering these little steps. Okay, but even if someone asks you that how you're going to find out, so you know the speed, right? And if you know the speed, you can actually integrate this speed for one time period. So the answer that you are going to get is going to be 8r. So hopefully this is all good to all of you. Please understand how we have found out speed at any given point, right? If again I'm telling you, if you're going to integrate it with respect to time for one time period, that is for 0 to t, right, you're going to get 8r, which is length of this cycloid path. Now moving on, let's suppose we are discussing about backward and forward slipping. We have discussed that if there was no slipping, in that case friction force wouldn't act, right? But let's suppose now friction forces, now there is a need for friction force to act. Let's suppose that initially this is V and V is actually greater than R omega, which is the case for forward slipping and the surface is rough. Now what's going to happen? The thing is, at this particular point, friction force will act, and friction force will act in the backward direction. This is where the friction force will act. And this friction force will actually, it will create a torque. And because of this torque, omega will get increased, right? So you must understand to write two types of equation. One is translational equation for translational motion, and one is for rotational motion. So for translational motion, this friction force is also creating a retardation for the velocity v, right? So this force can be actually written as mass times acceleration, right? And when we are going to talk about the rotational part, we are going to write actually torque, and torque will be written as F times R equals to moment of inertia of the body times alpha, right? Now, how to solve these kinds of equation? We are going to solve it using a case on an inclined plane. Let's suppose we have got an inclined plane and the angle of inclination is theta, and we have got a body and let's draw all the forces that we know. So we know that mg sine theta will act, and because of this mg sine theta, friction force must act in this direction so that pure rolling can be achieved. This is friction force, right? Now let's try to write all the equations that we can, right? So we can write two types of equations. First is translational motion equation. So translational motion equation can be written as mg sine theta minus friction force equals to mass of the body times acceleration, right? And please remember what is the condition for pure rolling. Pure rolling basically means v equals to r omega and acceleration equals to r alpha. These are the two cases, right? So the second equation will be for the rotational part, it will be friction force equals to, the torque generated because of friction force F times R will be equals to moment of inertia. And see, instead of writing as moment of inertia as I can also rewrite it as CMR square. CM CMR square. Now what is this CMR square? I'll explain it. See, what I'm trying to do is, we know that moment of inertia of, if we are going to talk about, let's say if you are going to talk about a ring. So for a ring, the moment of inertia is mr square. For a disk, moment of inertia is mr square by 2. For a hollow cylinder, moment of inertia is mr square. For a solid cylinder, moment of inertia is again mr square by 2, and so on, right? You can, so C in this case is going to be 1, in this case it's going to be 1 by 2, in this case it's going to be 1, in this case it's going to be 1 by 2. In case for a solid sphere it's going to be 2 by 5, in case for a hollow sphere it's going to be 2 by 3, and so on, right? So that's why I've written as CMR square. It is easier for you to remember. Now what we are going to do is, we know one thing, that acceleration can be written as, by the way, sorry, this is I times alpha, right? Now the next thing is, instead of writing it like this, I can cancel out one of the r. This is Cm, and instead of alpha I am going to write it as A by r, stating that we are talking about pure rolling. Pure rolling has been achieved, right? So friction equals to Cma. Let's put the value of this friction in this equation again. So this is going to be mg sine theta minus Cm times A equals to ma. So from here you can find out what acceleration is going to be. Acceleration is going to be g sine theta. I can cancel out all the m's, divided by, right, I've got over as 1 plus c. So 1 plus c. Now please look at this formula, and then I'll also share an important note for this. G sine theta divided by 1 plus c. I think, yeah. And then for solid sphere, it is c value is 2 by 5, right? Now acceleration is coming out to be g sine theta divided by 1 plus c. This means that acceleration inversely depends on c. So the rigid body which has got greatest c will have the least acceleration. Is that correct? So the largest c is for obviously for ring and for hollow cylinder, right? So their accelerations are going to be the smallest. So for ring and for hollow cylinder, then we have got disc and we have got solid cylinder. And then we have got hollow sphere, and then the largest acceleration is going to be of solid sphere. So this is a very important point. This means that if you are going to actually, this is a, now again this is a famous question. If you have got an inclined plane like this, and you are actually releasing you're releasing multiple objects from the top on different inclined plane, right? And someone is asking you that which body will reach the bottom first. So I mean the which has got the maximum acceleration will take the least time. Time for a disc and solid cylinder will be same, and for ring and hollow cylinder would be same. Please have a look, and that's all will be about pure rolling. So my dear friends, hopefully you have got this concept as well. So that was all about rolling motion. Now, in the next class, I'm going to come back with a new chapter. So for now, we have completed rotational motion. I believe that if you're going to go through all of these concepts again, you will be good to go for solving any other questions, right? So thank you so much. We'll meet you in the next class. Till then, take care. Bye bye.